Text, Indeed, One Search. All jobs. At Indeed Eng, monthly tech talks at Indeed's Austin headquarters, engineering.indeed.com. Engineering velocity, building great software through rapid iteration. Dan Heller.
I'm very excited to be here tonight to talk about engineering velocity and what it means to us here at Indeed, and specifically how we've enabled a culture of rapid iteration and delivery of new features and functionality in software. As Jack said, my name is Dan Heller. For the last 2 years, I've been an engineering manager here at Indeed, focused on our employer applications.
A circle around Dan in a group photo.
I joined Indeed in 2009 as a senior engineer and tech lead.
Text, I help people get jobs.
And since then, I've been helping people find jobs by building employer applications and making sure that employers can find the best candidates they're looking for on Indeed. For some background on Indeed, we're the #1 job site worldwide. More people find their jobs on Indeed than anywhere else. Every month, we have over 100 million job seekers who are doing over 3 billion searches. Before Indeed, I worked at Google as part of the Gmail backend team, working on storage systems and data management tools. And before Google, I was at IBM in the Systems and Technology group, working on software for processor development and simulation and verification. When I joined Indeed, the culture of high-performing teams and individuals and the commitment to delivering high-quality products were not new to me. What was new to me was the focus on rapid iteration. And to put things in perspective, at IBM, we were developing processors. And this is an industry that typically only releases major new architectures roughly every 2 years. At Google, my team was doing major feature releases about every 2 months with occasional bug fixes in between. At Indeed, we're releasing all of our software every week or even more often. And this means that every week we're taking all of the new features and functionality we've built, we're testing and verifying them, and we're putting them in production in front of our job seekers.
Rapid iteration leads to better products.
And it wasn't long after I joined Indeed before I realized that rapid iteration helps us build products that are better in every way. We've talked a lot about this in past tech talks.
Go. Indeed.com/DDPD.
In April, in our tech talk about data-driven product design, Chris Himes and Chris Garcia went in through our product design process and shared a lot of information about that. The video is available on our engineering blog, and I encourage you to go and watch it if you're interested in learning more. At the risk of massively oversimplifying everything presented there are 3 very important parts to our product development principles. The first is measure everything. We measure everything about how job seekers are interacting with our site at Indeed. Every click and every search are recorded. We can also measure how our software is executing on our systems. We can measure things like request times and memory usage for every request. Second, we test everything with A/B experiments. And we use a scientific method to evaluate every change to our site so we can understand how that change affects job seekers and how they use Indeed. Lastly, iterate quickly. We could quickly implement and evaluate ideas to understand if they're better for job seekers or not.
Lean Startup Cycle Flow Chart.
For many of you, this will sound familiar. This is very much like the build, measure, and learn from the Lean Startup cycle. And the idea is that you build a minimum viable product, you put it in front of your users and measure how they're interacting with it, and then you evaluate the data you collect, and you continue this process as you make small incremental changes. Many startups have been built with this model, and they've made great products for their markets. Indeed was also created with this model, and we still use it today. We do like to use the word deliver instead of build, though, to highlight that you can't begin to measure or learn about the changes you're making until we've delivered them to job seekers. This is in contrast to some software methodologies that will do frequent internal integration builds, but do less frequent deploys of those new features to their production environment. And Indeed, we've found that it's very important to quickly execute on this cycle. And by implementing it quickly, it accelerates our ability to make sure we're delivering the right product for users and job seekers. As I mentioned in past tech talks, we've talked about how we measure and learn and some of the ways that we are able to do those quickly.
Engineering velocity flow chart.
Tonight, I'm going to be talking about how we are able to deliver new functionality quickly to job seekers. And this is something that we've started calling engineering velocity. Very simply, engineering velocity is our ability to quickly deliver implementations of ideas to job seekers and employers. One aspect of engineering velocity that I'm not going to cover tonight is developer productivity, even though it is very important. Very simply, our approach to developer productivity at Indeed has been to choose appropriate technologies, manage our technical debt, and hire great engineers. Instead, I'll be talking about the things that Indeed has done in the areas of software architecture, processes and tools, and risk management that have accelerated our ability to deliver implementations of ideas to users. When engineers talk about software architecture, we often talk about things like security, availability, or scalability, or many other ilities. As our code base grew and as our team grew, we found it important to account for the ability to iterate quickly when designing our software systems. One of the things that we've done in this area is to move towards a service-oriented architecture. When Indeed first started working on job search, we had a small and focused code base in the job search web application. As a pragmatic startup, we looked for simple solutions to our problems. And so when it came time to deliver new features and functionality to job seekers, we would just implement that within the job search web app. And this code base grew over time until we had a large monolithic web app that we were releasing every week.
Elements of the job search web app: authentication, location, index search, doc retrieval, company info.
Internally, it was structured well into different modules that were focused on different pieces of functionality. This allowed us to have small teams that were focused on each of these modules. This wasn't enough, though. Because this was a large monolithic application, it needed to be released all at once. And so all of the teams needed to be ready to release at the same time. As an example, if we had a release candidate that we had in our QA environment, and we wanted to release it to production, but the index search team was working through a bug and was not ready to release, that would hold up the release of the entire application, even if other teams had new features and functionality that they wanted to get in front of job seekers. This added a lot of communication and collaboration overhead, but more importantly, it was reducing the rate at which we could get our software in front of job seekers. And so the solution was to move to a service-oriented architecture. By moving each of these modules into a separate component that we could release independently and on its own schedule, each of these teams was now free to put their features in front of job seekers when they were ready. This also meant that instead of one large and complex release, we could have many smaller, simpler releases, which gave us a much more predictable release schedule.
Technical challenges.
There were some challenges that we faced before we could move the job search web application to a service-oriented architecture. First, at Indeed, speed is a feature. And we can consistently generate search results pages for job seekers in 100 milliseconds or less. And so this meant, as we decomposed the job search web app into services, if the overhead of a service call was even a few milliseconds, that would significantly impact the page load time for job seekers. Second, we needed a solution that was both forwards and compatible for services. This meant that any client or any service provider would be able to be updated at any time. Without this compatibility, whenever we were evolving a service interface or making a change to the data in the service provider and client would need to be deployed in lockstep, which would erase a lot of the velocity gains that we were hoping to get from moving to a service-oriented architecture.
Red boxcar of a train. Text, Boxcar, high-performance SOA framework, http://go.indeed.com/boxcar.
Our solution to this problem was to build Boxcar. Boxcar is a framework for building high-performance service-oriented architectures. We've shared information about Boxcar on the Indeed engineering blog, and you can read in more detail about Boxcar there. There's two parts of Boxcar that I want to cover tonight. The first is how Boxcar is able to do load distribution without middleware.
In a diagram, lines run directly from 3 different clients to 2 different servers.
Boxcar has an algorithm and protocol that allows clients to distribute the load of their requests over the pool of available service providers. The ability to run without middleware cuts down on the amount of network communication and the network distance between clients and servers. This is a big part of how Boxcar is able to implement services with sub-millisecond overhead.
Protobuf, protocol buffers, Google's data interchange format. Represent complex data types.
The second aspect of Boxcar that I want to talk about is how Boxcar is able to provide API compatibility. Boxcar is built on top of Google protocol buffers. And protocol buffers is an open source library from Google that allows you to define data types and to serialize them in a platform agnostic way. This serialization is extremely compact and performant, but it can also be done in a way that's forwards and backwards compatible. This means that a serialized data structure can be deserialized by software that has a different version of the data type defined. And so Boxcar encodes all of the data in the request and the response using protocol buffers. This means we can evolve our service interfaces such that a new version of a client can talk to an old version of a service provider, and vice versa. When adding a new capability to a service interface, this compatibility makes it possible to release a new version of either the client or the server first, greatly reducing the deploy ordering dependencies when releasing, and also cuts down on our communication and collaboration overhead.
Railroad track graphics next to each element of Boxcar.
With Boxcar, we've been able to move many of our applications, including the job search application, towards a service-oriented architecture. More importantly, it's enabled us to deliver functionality more quickly to job seekers, even as our code base and our teams grow.
Links of a chain break apart.
And the real power of Boxcar is that it's allowed us to have a decoupled system architecture. Decoupling is a good principle in general in engineering, but more importantly, it allows us to have a high engineering velocity. In addition to needing to decompose our applications into services, we also wanted to do the same thing for our web front ends. We needed a service-oriented architecture for web front ends. And to really explain what I mean, let's take a look at some of the pages that we have available on Indeed.
Indeed search results for a software engineer in Austin, Texas.
Many of you are familiar with the search results page for job search, but we have many other pages for job seekers.
Walgreens page, city forums, a graph of job trends, a list of industry employment trends, a page displays software engineer salary in Texas, an average salary of jobs with titles matching your search. Best places to work in San Antonio, Texas.
We have company pages, discussion forums, job and industry trends, we have salary pages, and there's also the best places to work leaderboard. Each of these pages was very different.
Each page should have its own application.
It had different features, it accessed different data, there were different operational requirements, and we wanted to have a different team that could be focused on each set of functionality. And so just like all of the components in the job search, all the modules in job search, by splitting these up into separate components, we could have each team own it and work on their own schedule and provide new features to job seekers when they were ready.
A double-headed arrow between a folder and a column of text, navigation, authentication, activity tracking, security, URL rewriting. Lines from the first column connect to a second column of text, job search, trends, company info, forums, salary.
On the other hand, there was a lot of functionality that was common to all of our web applications. Navigation and authentication are two very user-visible things that we wanted to be common. But there were less user-visible things that should be common, like activity tracking, security, and URL rewriting.
The name, Indeed, replaces all the text in the first column.
And even though we wanted to decompose our site into many web apps, to a job seeker, they needed to all be part of Indeed. And there should be a consistent and coherent user experience as they move between all of the parts of our site.
One implementation of shared functionality.
And so these were the technical challenges that we faced in decoupling our web front ends from each other. One option that we considered was having shared code libraries to implement the shared functionality. This is actually an option that we did not go with, and we had some concerns about it. First is we felt it would reduce the flexibility of technology decisions for the teams working on each web app. And what I mean by this is if the shared library was implemented in Java, then all of our teams would be forced to implement their web front ends in Java. And even though we have largely standardized on a Java stack for building our web front ends, we thought it was important that each team can make technology decisions that are appropriate for the problems that they're facing. Also, using a shared code library would have involved a release of every single project whenever we had a change to that library. And although we have invested in making our releases easier and faster, we didn't want to create unnecessary work. Also along those lines, whenever a change to that library was a user visible change, there would be an inconsistent user experience across all of our pages while we were in the process of releasing the new library. We were able to address all of these challenges by creating an application-level HTTP proxy, which we call NavShell. This allows us to have separate web apps for each set of pages and to have NavShell sitting in front of them, providing a single implementation of shared functionality and also an implementation of user-visible features like navigation.
In a flowchart, an arrow points from request to NavShell and from NavShell to web app.
Because NavShell is primarily a proxy, it uses HTTP to fetch content from each web app. This means that each web app can be built using the technologies that are most appropriate for that team.
Johnson & Johnson's company page on Indeed.
Here's a company information page, which is served by the company page's web app via the NavShell.
A blue border around the main content. An orange border around Indeed's job search windows.
The part in blue is generated by the company page web app, and the part in orange at the top of the page is generated by NavShell. NavShell assembles all this content together and returns it to the browser in a single page.
Computer code in black, then in orange and blue.
Here's what that page would look like to your browser. I've removed some of the details so that it would fit on one screen. Again, in orange, you see the part of the page that would be generated by NavShell, the consistent navigation at the top of the page. In the middle of the page is the body of the page, which is generated by the company page web app. There are other parts of this page that needed to be generated by the company page web app, though. Things in the head section, such as the page title or CSS or JavaScript files that needed to be loaded, also need to be mentioned there.
Request headers, cookie, user agent, referrer, etc. Xindeed shell, referrer, 1, Xindeed logged in, 01, Xindeed email, chris@indeed.com, Xindeed locale, and _US, Xindeed geo, US. In a diagram, two arrows flow to and from NavShell and web app.
This is handled by using HTTP request and response headers. When the NavShell makes the request to the company page web app, it includes HTTP request headers. So some of the standard headers that it got from the browser, such as the user agent, the referrer, and things like that. But it also defines, we have custom headers defined specific to NavShell that include the results of the common functionality that NavShell has implemented. So whether or not the job seeker is logged in, their email address, and their preferred language. When the web app responds to NavShell, it includes the content of the page on the HTTP response body, but it can also use HTTP response headers to set things like cookies, but also to provide directives to NavShell that will affect how it generates the rest of the page and assembles all the content together. NavShell has been a simple solution to our problem. It means we have no duplicated code for all of the shared functionality in web apps. We have a centralized place where navigation changes happen, and we can make them happen across the entire site all at once. By using plain HTTP with a strong contract on the request and response headers, we've freed up the teams working on individual web apps to make the technology choices that are right for them. More importantly, we've created the ability to decouple all our site into many different front ends that can be released on their own schedule.
In a flowchart, an arrow points from requests to NavShell. From NavShell, an arrow points to web apps, and railroad tracks run to services. From services, tracks run to web apps. And
so when we use both NavShell and Boxcar throughout Indeed, we end up with a system architecture made up of many small and independent components. Many of the changes that we need to make as we release new features for job seekers are limited to one or two components, and we can release those components when we're ready without affecting the rest of the system. Another example of an architectural decision that I'd like to talk about where we made the decision to increase our engineering velocity has been how we use web-based delivery of features within our native apps. The mobile job search experience is really important to us as more and more job seekers are going online to find jobs, or sorry, to use touch devices.
Indeed's mobile interface.
We started working on mobile, and we first started by building a mobile-optimized version of web job search. And when we started building mobile apps, most of the functionality within the app was delivered within a web view embedded in the app.
Side by side, the Indeed interface for its mobile browser and its mobile app.
We made this decision so that we could have a single code base for all of our mobile platforms, and it also allowed us to quickly deliver new features within mobile to all of these platforms at the same time.
A list of Java jobs on both the mobile browser and mobile app.
And so now, when we typically implement a new feature, we're delivering it within the web view if possible, and we're only implementing it with native code when we need to. And since we've originally launched our mobile applications this way, the approach to deliver most of the functionality within the web view has now become a strategic part of how we're able to iterate and build mobile products.
Desktop browsers, and mobile app on a flowchart. Double-headed arrows between desktop browsers and the web app, and between the web app and shared services. Double-headed arrows between a different web app, and the mobile browser and apps, along with web services.
And so we have shared infrastructure that's used by both the desktop web search application as well as the mobile web search application. But the mobile web search application is used to provide functionality for both mobile web and mobile apps.
Shared code across platforms.
And so we have one code base for mobile web, iOS, and Android applications. And we can release features on all of these platforms at the same time.
Release on our own schedule.
This also means we don't have to wait for App Store approval, or we don't have to wait for job seekers to upgrade to the new version of our application when we want to deliver new functionality to them. We're able to do it on our own schedule.
Easy to run experiments.
We also are able to do A/B testing more easily. Implementing A/B tests within native code is challenging. And by doing it within a web view, we were able to reuse all of the existing frameworks and systems we had for performing and evaluating experiments.
Deliver, processes and tools.
Now I'll talk about one of the processes that we've automated at Indeed, specifically our translation process, in order to increase our engineering velocity.
World map.
Indeed is a global company. Our products are available in 28 languages, and we have 55 international sites.
The phrase, one search. All jobs, in different languages.
Making our products available in 28 languages is certainly an investment, but we want to help everyone get jobs, not just English speakers.
Flowchart before internationalization. Implement, commit, deploy to QA, verify, deploy to production.
Before we started internationalizing our products, our development process was extremely straightforward. We would implement a new feature, commit it to the source code repository, put that in our QA environment when we were ready, verify that it was working correctly, and then we could put it in our production environment.
Internationalization process overhead, implement, commit, extract, translate, commit, deploy to QA, verify, deploy to production.
After we started internationalizing, the process got more complicated. For user-visible changes, we needed to extract all of the new text in the UI. We needed to translate it into every language that we support, and we needed to then commit all of those changes. Additionally, we needed to verify that these changes worked correctly in all the languages that we support. Typically, this was adding 1 day to the amount of time that we needed to deliver a new feature. This may not sound like much, but when you're releasing every week or more often, this is 20% or more of your development cycle time.
The world map.
And so there were times when we would choose to release a new feature or experiment sooner instead of waiting for that feature to be translated into every language.
The map highlights only the United States.
This resulted in some experiments being rolled out for US English only.
I help English-speaking Americans get jobs.
And although this allowed us to iterate quickly, it meant that we'd be making product decisions and crafting product strategy based on the behavior of English-speaking Americans instead of the whole world. We needed a way to quickly deliver all of our new features in 28 languages. We first looked into machine translation. This seemed ideal. We could commit a change to the UI, extract the text that was visible to the users, and within seconds, we'd have the translated text.
Machine translation from English to Portuguese.
The results were not as good as we hoped, though. And in many cases, they were unacceptable. For example, here, we're using the word cadastrado to ask users if they're registered. And in Brazil, a job seeker would understand what we're talking about. A job seeker from Portugal, on the other hand, would wonder why we're asking if they have a criminal record. And so although low-quality translations are better than no translations, they weren't good enough, and we needed to do better.
Human translation service, 1-hour translation.
We were able to identify and incorporate a human-powered translation service. 1-hour translation provides an API that we can use to request the translation of a piece of text. Someone at 1-hour translation will perform the translation, and we have a separate API that we can use to retrieve the translated text when it's available. The results are not actually always available in 1 hour, but generally we found that it's fast enough that it doesn't slow down our development process.
Tuesday afternoon, commit code, fetch machine translations.
And so now we combine these two translation mechanisms. For example, if we commit code on Tuesday, we can immediately fetch machine translations, and they'll be available in our continuous integration environment, and they can be tested there.
Wednesday morning, retrieve human translations.
At the same time, we'll request human translations. And then later that day, or maybe the next morning, we can retrieve the results, and we can use them in our QA environment to verify that the new feature is working in all languages.
A flowchart depicts localization before translation automation. Implement, commit, extract, translate, commit, deploy to QA, verify, deploy to production. A new version eliminates the commit step.
And so this automation has allowed us to simplify the work needed to translate our products to just a few steps that are highly automated. The result is a simpler and less costly process.
I help everyone get jobs.
And so now we can deliver new features worldwide, and this increases our engineering velocity. It also means that we can make sure we're building the best products for the entire world.
Deliver, risk management.
The last area I'm going to talk about is risk management. Anytime you're making a change to your production environment is the chance to introduce a negative impact for our job seekers. There are many factors that affect the risk associated with a change. Things like the probability of an issue, the duration of the issue, and the number of users who are affected by it.
A chart depicts the number of releases. It stays flat from 2007 to 2008, then rises in 2009, 2011, 2012, and 2013.
As we moved towards a decomposed system architecture, we had more components and we were releasing them more often. And so it became important that we manage the risk associated with each release. One benefit of having smaller releases is that there was less functionality in each one, and there was less chance for a bug or a regression to be introduced. We also increased our monitoring so that we could quickly address any issues and reduce the amount of time that they were impacting job seekers. We use a third-party service called Datadog to get a real-time view of business and system metrics across all of our products in all of our data centers.
Datadog graphs.
Here you see an example of what this view looks like for one of our applications. We can see page load time, CPU and memory usage, thread counts, and other things like that.
Real-time monitoring with Datadog.
With Datadog, we have an agent that runs on all of our servers and is examining in real time our access and application logs and sending summarized data back to Datadog. We can then view system and customized metrics, including page load times, the number of searches performed, and the number of jobs that job seekers are viewing and applying to. And we can do this all in customizable dashboards. We've also created a Healthcheck Framework that allows applications to report their internal state and health. And this allows us to know when individual instances are not able to fulfill job seeker requests. Using this system, we've also been able to divert traffic away from unhealthy instances of services. We've also been able to implement graceful degradation to disable features for failing dependencies, so that instead of returning error pages when a dependency is unavailable, we return a results page that simply has less functionality enabled.
Monitoring and alerting, identify runtime issues.
We also use Nagios to monitor the results of all the health checks. We can quickly identify any issues that are affecting job seekers and address them. And Nagios also manages the alerting of our ops team when there is an issue.
Proctor.
Another way that we manage risk is with a system we call Proctor. Proctor is a data-driven system for managing A/B tests that we've created here at Indeed. It allows us to dynamically define rules to segment visitors and assign test groups. Proctor also allows us to manage the visibility of new features. We originally created Proctor as a way to manage our A/B experiments that we're doing. But we found that we can use it to more generally dynamically manage the behavior of our applications.
Codes Proctor can use.
And so the logic to determine which behavior we should use for when fulfilling a request is dynamic and can incorporate any criteria we need to segment the visitors. Some examples are if a job seeker is logged in, the device or the browser they're using, their country or language. Proctor also has the ability to randomly determine the behavior for a visitor who meets specific criteria. And so anytime we need to have multiple behaviors implemented within our code, a simple check is used to determine which behavior should be used for the given request. Under the covers, Proctor is examining all of the rules that are defined and determining which behavior we should use.
Feature toggles, probability of issue.
Proctor has allowed us to implement feature toggles. Feature toggles allow us to have all of the functionality for a new feature implemented but disabled at runtime in code paths that won't be executed. We can then build a large feature over the course of several releases with the code paths disabled, and we can launch it internally for users for Indeed employees. And when we're confident that the feature is ready for job seekers, we can then change the toggle and release it to job seekers. This allows us to have more confidence that a feature will work correctly in our production environment.
Duration of issue.
Proctor also allows us to decouple features from releases. This means that we can release a new version of our software with a new feature disabled. We can wait and monitor the new version of the software, make sure that it's performing well and that it's healthy, and only then enable the toggle that will start showing the new functionality to job seekers. If we do notice any issues, we can very quickly disable the new feature without having to roll back the software.
Number of users affected.
Proctor has also allowed us to make lots of small allocation changes to group sizes when rolling out new tests or features that we consider especially risky or possibly resource intensive. We can enable a new feature for 1% of our traffic, and then later 5%, 10%, 20%, all the way up to 100% in a day or even just a few hours. This allows us to very early on identify when there are bugs or possible scalability issues when they're only affecting a few users and before they're affecting all of our job seekers. We'll be talking more about Proctor in our next Indeed Eng Tech Talk on October 2nd, and we'll have more information about that later.
Deliver, software architecture, processes and tools, risk management.
These are just a few of the examples of how Indeed has increased our engineering velocity by addressing the challenges we've faced in delivering new software quickly. As a developer, rapid iteration has really given me what I was looking for. I have more confidence that the code that I'm working on will have a positive effect on my product, and that I can deliver more value for job seekers and employers. Likewise, there's an increased chance of success for the projects I'm working on. I like to say that Indeed has no failed projects, or at least no big failed projects. We are able to quickly put our ideas in front of users and understand if this is a good product for job seekers or not. And we can avoid large investments in bad ideas. This means we can fail fast, learn from the experience, and move on to something that's going to be more valuable. We also have very few deadline crunches. When you release frequently, it's easier to have the mentality of, we'll ship it when it's ready, rather than rushing to meet a deadline. And this is because the next release is only a few days away. So if I miss this week's release, that's OK. It'll be in a few days or next week. This approach also means we can have more transparent schedules. When working on large changes, we can break up that large change into several small changes, be pushing them to our production environment all the time, disabled with feature toggles.
Large changes hidden behind feature toggles.
And we can be constantly validating that they work in our production environment.
Incremental progress validated in production environment.
And so we can know as we go through the project that everything we've built is working, and we don't have to worry about testing it again when we integrate everything together. We've built all of this. Everything I've discussed tonight has been built incrementally, just like our products, to meet the challenges we've faced as we increase our engineering velocity. The challenges you face and your solutions to them will be different from ours. In physics, velocity is defined as the distance you can travel in a certain amount of time. And by iterating rapidly and delivering features quickly, we've been able to increase our engineering velocity here at Indeed. Thank you.
The audience applauds. Indeed, one search. All jobs.